In this video, we're going to look at some of the similarities and differences between matrix addition and multiplication and how those things interact, and ordinary real number or complex number addition and multiplication. So to begin with, here are some of the similarities. Actually, there's some similarities and one oddball here, which I'll mention in a moment. So first of all, matrix multiplication is associative. So the associativity property you've seen a lot of times before. In this case, what it says is that if you've got any three matrices A, B, and C such that A times B makes sense and B times C makes sense, then A times B times C is the same as A times B times C. Secondly, there are a couple of distributivity properties which tell you how matrix addition and matrix multiplication interact with one another. So if you have two matrices, A and A prime of the same size, and if the product A times B makes sense, then A plus A prime times B is the same as A times B plus A prime times B. There is also another distributivity law where the addition happens on the other side of the matrix multiplication. Thirdly, there's a kind of associativity property for scalar multiplication and matrix multiplication that says if you've got a number, a scalar, lambda, so a scalar just means a number here, then lambda times A multiplied into B is the same as lambda scalar multiplied into the matrix product A times B, and that's the same as A times the scalar multiple lambda B. And then finally, there's a identity which doesn't have any kind of parallel for real numbers or complex numbers because it involves the transpose, and there isn't a transpose for real or complex numbers. And what it says is that A times B all transposed is the same as B transpose multiplied by A transpose. So something really interesting is happening in there because the multiplication happens in the opposite order on the two sides of this equality. So on the left it was A times B, on the right it was B transpose times A transpose. So something is certainly happening there. In fact, you will prove this yourself on coursework 3. Okay, I'd like to do a proof of one of these to practice using summation notation because it can be quite difficult to do this correctly sometimes. So I'm going to prove part 1. If you'd like to see proofs of the other parts, then you can find them as usual in the lecture notes for Algebra 1. So let's have some notation. Let's fix that A will be the matrix whose ij entry is written like this, lowercase a subscript ij, and B similarly will look like this, and C will look like this. And I notice that both A times B times C and A times B times C, both of those things are matrices of the same size. They're both M by Q matrices in the notation of this proposition. So all we need to do is check that for any I and for any j, the ij entry of the left-hand side of 1 is the same as the ij entry of the right-hand side. So let's start by thinking of the right-hand side. I want to know what is the ij entry for a given I and j of the matrix product A times B times C. So to do that, to work that out, I'm going to need to know what the ij entry of AB looks like. So let's write that down because we can just write down the usual formula for matrix multiplication. So the ij entry of AB is the sum from k equals 1 up to n of A, I, K, B, K, J. Now we know that, we can work out the ij entry of A times B times C. So what do I need when I do this? Let's think carefully about what we're going to have to do here. We're going to have to do a summation. And the question is, where does the summation go? So the summation should go down the rows of C. The summation should go from 1, 2, 3, 4, 5 up to P, because P is the number of rows of C. So I can't use the dummy variable k again, because I'm already using the dummy variable k in my expression for the ij entry of AB. So let's use a different dummy variable. Let's say L equals 1 up to P. And then I should multiply together the kj entry of C, sorry, the lj entry of C. So it should be C lj, because L is the dummy variable we're using in this summation. Then I need to multiply that by the IL entry of AB. So the IL entry from AB should be obtained just by putting L in place of J in the expression that we wrote down just here. So what I will have is another sum from k equals 1 up to n. Then it will be AIK, to make that a bit clearer, AIK BKL. Okay, so the sum from L equals 1 to P of the sum from k equals 1 to n of AIK times BKL times CLJ. Okay, so we've got this expression for the ij entry of one side, the right-hand side of our supposed equality. Let's now do the other side. So to work out the left-hand side, I need to start with the ij entry for BC. So the ij entry for BC is, well, again, it should be a sum. And this time we should be summing again down the rows of C. So we'd be multiplying rows of B into columns of C. So there should be one term in the sum for each row in C, because we go down the rows of a particular column. So again, there should be a sum over 1, 2, 3 up to P. And this time I'm going to keep L as my dummy variable again. So L equals 1 up to P. I mean, it doesn't matter what you call the dummy variable. That's why it's called a dummy variable. But I'm going to keep it as L this time. So the ij entry for BC will be the sum of B, I, L, C, L, J, like this. So let's work out now the ij entry of A, B, C. So I should have a sum. So let's have a dummy variable called k this time. We're multiplying A into something, so we're going to need our summation to go from k equals 1 to n, because n is the number of columns that A has and the number of rows that B times C has. And then we should have AIK times the kj entry of BC. So the kj entry for BC, well, I just need to replace I by k in that expression I wrote down before. So this times the sum from L equals 1 to P of BKL CLJ. Okay, well, we can multiply this AIK through the sum if we like to get, and let's just write this carefully, sum from k equals 1 to n times of the sum from L equals 1 to P of AIK times BKL times CLJ. And if you look, that's not quite exactly the same as what we got before. It's very nearly what we got before, but it's not quite the same. So the things that we're adding up are the same both times. You've got AIK, BKL, CLJ multiplied together both times. The only difference is the summations. So here you've got the K summation and then the L summation. And here you've got the L summation and then the K summation. But that doesn't matter because you're just getting the same terms in a different order. Okay, so we have proved for any I and j that the ij entry of A times B times C is the same as the ij entry of A times B times C and that means that those matrices are equal. So this is how we go about proving that two matrices are equal. First, you check that they really do have the same size, and both of our matrices were M by Q, and then you check that for each I and j, the ij entry of one of the matrices is equal to the corresponding ij entry of the other matrix. And we've done this, so we know that this equality really is true, really is an equality. Okay, so let's look at some of the ways in which matrix multiplication is not similar to real number or complex number multiplication. And the first way in which it is not similar is that matrix multiplication is not commutative. So even when both of the products A times B and B times A make sense for two matrices A and B, the answer that you get might not be equal. In fact, if you try this with square matrices, then if you just choose some examples completely at random, then it's extremely likely that they will be a counterexample to matrix multiplication being commutative. So let's just look at the example which I've written here. We've got two 2 by 2 matrices multiplied together in both orders. So first of all, we have 1, 2, 3, 4 times 5, 6, 7, 8. So if I work this out, I've got 1 times 5 plus 2 times 7, which is 19. Then I've got 1 times 6 plus 16, which is 22. And then 3 times, so 15 plus 28, which is 43. And 18 plus 32, which is 50. Okay, let's do the other order. So we've got the same matrices but multiplied together in the opposite order. So this time, I'm just going to work out one entry. I'm going to work out the 1, 1 entry, and I've got 5 times 1 plus 6 times 3. So 5 plus 18. So this is 23. Okay, well, whatever happens, these are not equal, because you can see that they don't even have the same 1, 1 entry. Those are not equal. So matrix multiplication is not commutative. So it's very important to remember this. When you're multiplying two matrices, it really matters what order you do it in. Okay, but things are even worse than this, because in the real numbers, or the complex numbers, you can't, for example, multiply two non-zero numbers together and get the answer 0. You can't multiply two non-zero complex numbers and have the answer be 0. You can't multiply together two real numbers which weren't 0 and get the answer 0. But it can happen for matrices that you take a matrix and you multiply it by another matrix and you get the answer which is a 0 matrix, even though neither of the two matrices you multiplied together was the 0 matrix. So for example, let's look at this matrix here, 0, 1, 0, 0. We're going to look at that square of that matrix. So 0, 1, 0, 0 times 0, 1, 0, 0. And if you work this out, you find you get 0, 0, 0, 0. So when you multiply two matrices together, the answer can sometimes be the 0 matrix, even when neither of the factors in that product were the 0 matrix. And this is related to the fact that not every matrix is invertible. So if you give me a real number, for example, let's say x is in R, a real number, and x is not 0, well then there is a real number 1 over x, with the property that it is a multiplicative inverse for x. In other words, 1 over x times x is equal to 1 again. Now, there is no similar property for matrices, so you can't divide in general by matrices. So this property of invertibility is important enough that we're going to discuss it in detail in the subsequent video. Okay, but let's look at finally one way in which matrix multiplication and ordinary real number multiplication are similar, and that's in the existence of something which behaves as what's called a multiplicative identity. So in real numbers, the multiplicative identity is the number 1, and in the complex numbers, the multiplicative identity is the number 1. What that means is when you multiply something by 1, you don't change the thing you multiplied by 1. So 5 times 1 is 5, and 7 times 1 is 7, and so on. And there is a matrix, in fact there is a family of matrices which have the same kind of property for matrix multiplication. And that family of matrices is called the family of identity matrices. So the definition here is that the n by n identity matrix, which we write like this, is the n by n matrix with ij entry, which is 1 if I is equal to j and 0 otherwise. So it's got 1s on the leading diagonal. That means the 1, 1 entry and the 2, 2 entry and the 3, 3 entry and so on. And then it's got zeros everywhere else. So for example, I2, the 2 by 2 identity matrix, would have a 1 in position 1, 1 and a 1 in position 2, 2 and zeros everywhere else. And the 3 by 3 identity matrix would have a 1 in position 1, 1 and a 1 in position 2, 2, a 1 in position 3, 3, and it would have zeros everywhere else, and so on. So we usually write I with a subscript, like IN, to mean the n by n identity matrix, but sometimes we'll just be lazy and write I. Well, when I say we, I mean I will just be lazy and sometimes write I when the size of the matrix we're talking about is clear, like when only one such matrix would make sense. Okay, so what I was claiming was that this identity matrix behaved like the real number 1 does under multiplication. So if you've got any m by n matrix A, then if you multiply it by the identity matrix on either side, then you just get A back again. Okay, so let's prove one of those equalities. So which one should we do? Let's do the first one. So we're going to prove that Im times A is equal to A again. So we need some notation. So we'll let the ij entry of A be A subscript ij, and let's look at Im. So we're going to introduce some notation for the ij entry of the m by m identity. So let's call this dij, and then from the definition of the identity matrix, dij is going to be equal to, well, it will be 1 if I was equal to j, and it will be 0 if I is not equal to j. And then we're going to work out Im times A, and we're going to see that the ij entry of Im times A is the same as the ij entry of A for any I and any j. And since those matrices have the same size, they're both m by n, then they're then going to be equal. So we will show that for any I and j, the ij entry of Im is equal to, well, the ij entry of A, which in our notation is just this. So to do this, we've got to use the formula for the ij entry of a matrix product. Oops, what did I do? I missed out the letter A there, didn't I? That's better. Okay, so what's happening? We've got to use our formula for matrix products. So the ij entry of a matrix product Im times A is the sum from k equals 1 to m. Since we are multiplying the square m by m matrix Im into A, and m is the number of columns of Im and the number of rows of A, so then we should have the ik entry of our identity matrix, so dik, times the kj entry of A, so akj. Okay, but let's think what happens here. So most of those d subscript ik are equal to 0. So most of those terms in the sum are actually 0 because there's 0 times akj, and 0 times anything is 0. So most of the terms in the sum are 0. Except, so dii is the only one of these things, dik, which can be non-zero. So it's only when k is equal to I that dik would be non-zero. And in that case, dik is equal to 1. So what is the sum? Well, we can forget every term except the term when k is equal to I. And when k is equal to I, we get dik, which is 1 times aij, which is aij. Okay, we've shown that for any I and for any j, the ij entry of the identity times A is the same as the ij entry of A, so the identity times A is equal to A. If you want to see the proof of the other equality, you can find it as usual in the lecture notes for Algebra 1.